Hey there, everybody. Welcome back. We're in Calculus 3. We're using Anton's 11th edition book. For Calculus, this is Divergence Theorem. We are looking at the Divergence Theorem and how it applies to the inverse square fields that we've been talking about. So as you recall, the inverse square fields are some constant divided by the magnitude of r cubed times r. And so if we do treat S as some closed orientable surface around that, surrounding the origin, we're going around the origin, we can show that the flux through that surface is 4 pi times the constant. Okay, so that's all for any inverse square field. This is what it's going to boil down to. C changes, and it's got to be around the origin. We got to center it around the origin. So let's just walk through it. We've got E being our region between two surfaces. The outside surface could be anything. I drew a circle going outward with, so the positive orientation is outward. We want the region in between. I did a circle of radius A right here. That's going to be a radius A, R equals A right there. But we're looking for the field, the surface we're looking for, the solid we're looking for is between these two spheres or circles. So we got to do N1 going inwards because that's the direction it's pointing. It's pointing away from where the volume is. Okay, so we apply our divergence theorem. This integral up here is the divergence of F. And so we can break this up into two parts, F dotted with negative N1 and F dotted with N2. So we're going to assume that divergence is 0, like we can prove for the electric field E equals 1 over Q F, where F is an inverse square field written over here. EQQ is two different charges over the magnitude of R cubed times R. Some books use X, so you'll see magnitude of X cubed in the X direction. So our force is this, and if we apply the 1 over Q to this, we're going to see the E is just our electric field. E is E times Q over the magnitude of R cubed times R. This is our constant. This is what we should see when we do the 4 pi C. Okay. We're doing a radius A, keep that in mind. And that sphere is centered at the origin. This is easier to prove in spherical since E is only radial. The direction is only outward. And so the divergence of E in spherical coordinates is this. Okay. It's good to know. You know, maybe one of these semesters I'm going to have students calculate this. Maybe we'll look at calculating. Maybe it's a bonus question on the test. Calculate the divergence theorem for a spherical coordinate system. All right. So since our electric field is only going out radially, the partial derivative with respect to phi or theta is 0. So this goes to 0, that goes to 0, and we're really only looking at that component. So we've got the divergence of F, and we had it over two surfaces. We said it was equal to 0. So, and one of these had a negative in it, the N1 was negative. So we can move them to the other side. We're working with E, so F is now E. So E dot N, here's our E, EQ over the magnitude of R cubed times R. N is radially outward, so it's the radius vector divided by R. So when we dot these, we get EQ over the magnitude of R to the 4th power. But R dot R, if you remember when we went back to when we first did dot product, that was how we came up with the magnitude of R. It's the dot product of it with itself. So the R dot R will cancel out 2 of these right here. and we get EQ over the magnitude of R squared. Recall that magnitude of R is A though, since the sphere is radius A. That's our inner sphere. So that's just A squared on bottom, and this is all a constant now. So E dot N ds is going to be just the surface integral of ds. We pull the constant out, EQ over A squared outside. But we know what this is. This is a circle. I'm sorry, it was a sphere. And we know the surface of a sphere has the formula 4 pi r squared. Or you could work it out using theta and phi. But you could go with 4 pi r squared. R squared is A squared, so 4 pi A squared times EQ over A squared. We get 4 pi times EQ. Remember, C was our EQ, and we got it. We got our 4 pi EQ. So that's the electric flux. The electric flux of E is 4 pi EQ, which is Q over E naught, because that's what E is listed as. And this is through any closed surface containing the origin. The outer surface we didn't describe, it was just S2. The inner surface was radius A, but we were able to see that they are equal to each other right here. So any surface enclosing the origin for the electric flux will be the 4 pi EQ. That's it for this video. We got one more. Peace.